Our solar system is a busy place. It's filled with planets, moons, and asteroids. Each one follows a set of rules. They all orbit the sun. Most of them spin like tops as they travel. Imagine a spinning top, twirling almost perfectly upright. That's how most planets behave. They have a north pole and a south pole, and they spin around an imaginary line that connects these poles. This line is called the axis. For most planets, this axis is nearly vertical compared to their path around the sun. This predictable spin gives them their day and night cycles. But then, there's Uranus. Uranus is different. It doesn't play by the same rules as its neighbors. This distant ice giant is the odd one out in our celestial family. While other planets are like neat, upright spinning tops, Uranus is a rebel. It's as if something knocked it over a long, long time ago. Its spin isn't upright at all. Instead of spinning, it seems to roll along its orbit. This strange behavior makes Uranus one of the most fascinating and mysterious objects in our entire solar system. Let's take a tour of our planetary neighborhood. Starting from the Sun, we see Mercury, Venus, Earth, and Mars. These are the rocky inner planets. They all spin in a more or less upright fashion. Then we move to the gas giants. There's massive Jupiter and the beautiful ringed planet Saturn. They too spin with a respectable upright posture. They follow the general pattern. This pattern is believed to be a leftover from the formation of the solar system itself, a cosmic memory of the spinning disk of gas and dust that created everything. Uranus completely shatters this neat and tidy picture. It's the Great Anomaly. Its sideways rotation makes it unique among all the major planets. While the other planets politely spin, Uranus rolls. This means that for parts of its long 84-year orbit around the Sun, one of its poles points directly at the Sun. That pole experiences 42 years of continuous daylight. At the same time, the other pole is plunged into a dark, frozen winter that lasts for 42 years. The story of Uranus's discovery is itself a tale of surprise. It was the first planet found using a telescope. In 1781, an astronomer named William Herschel was scanning the night sky. He wasn't looking for a new planet, he was simply mapping the stars. But he noticed a faint object that seemed to move against the background of fixed stars. At first he thought it might be a comet, but as he and other astronomers tracked its movement, they realized it was something much bigger. It was a new planet, lurking in the cold, dark outer reaches of the solar system. In 1787, just 6 years after finding the planet, William Herschel discovered its two largest moons, which were later named Titania and Oberon. This was a crucial piece of the puzzle. The orbits of a planet's moons hold vital clues about the planet itself. In our solar system, the major moons almost always orbit above their planet's equator. But Uranus's moons did not. Their orbits were not flat relative to the solar system. Instead, their paths were tilted almost vertically. This could not be a coincidence. The moons were dutifully orbiting around Uranus's equator, just as moons are supposed to do. The problem was that the entire Uranian system was tipped over on its side. As astronomers grappled with the mystery of Uranus's extreme tilt, one idea began to gain more traction than any other. It was a theory born from the understanding that the early solar system was not the calm and orderly place we see today. Instead, it was a chaotic, violent shooting gallery. In its youth, our planetary neighborhood was filled with countless small bodies called planetesimals and larger ones called protoplanets. These objects were constantly crashing into one another, merging and growing in a process called accretion. This violent history provided the perfect backdrop for a truly dramatic explanation, the giant impact hypothesis. This theory proposes that Uranus was not born sideways. It was knocked over. The hypothesis is simple in its concept but staggering in its scale. It suggests that sometime during its formation, billions of years ago, the young Uranus was struck by another massive object. The impacting object would have been enormous, likely a protoplanet itself, perhaps 1 to 3 times the mass of the Earth. This rogue world, careening through the outer solar system, would have slammed into Uranus at an incredible speed, likely tens of thousands of kilometers per hour. The sheer force of this impact would have been enough to dramatically alter Uranus's rotation, tipping its axis over to the extreme angle we see today. A collision of this magnitude would have been a world-shattering event. The impactor would have likely been obliterated, with much of its material being absorbed by Uranus or blasted into orbit around the planet. The debris cloud from this colossal smash-up could have then coalesced to form the system of moons and rings we observe today. In the history of Uranian exploration, one event stands out above all others: the flyby of NASA's Voyager 2 spacecraft. Launched in 1977, Voyager 2 was on a grand tour of the outer solar system. On January 24, 1986, after a journey of nearly 9 years, humanity got its first and, so far, only close-up look at Uranus. For a few brief hours, the robotic probe sped through the Uranian system, its instruments frantically gathering as much data as possible. It discovered 10 new moons, all orbiting within the same tilted plane, and found 2 new rings. Most bizarre was Uranus's magnetic field, tilted by 59 degrees and offset from the planet's center. The data from Voyager 2's brief flyby provided a treasure trove of information that scientists are still analyzing decades later. It gave us the ground truth, the hard data against which all theories and simulations must be tested. It remains our only direct visit to this sideways world. In the years since the Voyager 2 flyby, our ability to probe the mysteries of Uranus has grown immensely, not through new missions, but through the exponential growth of computing power. The latest research findings are coming from increasingly sophisticated supercomputer simulations that can model the ancient giant impact with breathtaking precision. A groundbreaking study from 2018, led by researchers at Durham University, ran a series of high-resolution simulations of the cataclysmic collision. Their simulations showed that a glancing blow from an impactor roughly twice the mass of Earth could indeed have knocked Uranus onto its side in a matter of hours. More importantly, the model provided a fascinating explanation for one of Uranus's other oddities: its extremely cold temperature. The simulation suggested that the impactor created a thin shell of debris just below the atmosphere. This shell acts like a thermal blanket, trapping heat from Uranus's deep interior and preventing it from escaping into space. Despite the success of modern simulations, Uranus continues to hold on to some of its most profound secrets. One of the most persistent and puzzling mysteries is the planet's internal heat, or rather, the lack of it. All the other giant planets radiate significantly more heat into space than they receive from the sun. Uranus breaks this rule spectacularly. It is almost perfectly in thermal balance with the sun, meaning it has little to no measurable internal heat flow. This makes it the coldest planet in the solar system, with cloud-top temperatures plunging to a frigid -224 degrees Celsius. However, newer observations from Hubble and the James Webb Space Telescope are revealing a much more dynamic world, with powerful storms and changing cloud patterns. How can such an active atmosphere exist on a planet with so little internal heat? The exact mechanics remain a mystery. As powerful as our telescopes and computer models are, they have taken us as far as they can. To truly solve the remaining mysteries of Uranus, we need to go back. For this reason, the scientific community has made a mission to Uranus a top priority. The Uranus Orbiter and Probe was named the highest priority large-scale mission for the next decade. The proposed mission would be ambitious. It would involve a spacecraft that would go into orbit around Uranus for several years and carry a probe that would plunge directly into the planet's atmosphere. This atmospheric probe would directly measure composition, temperature, and pressure, providing ground truth needed to understand the planet's missing heat. The orbiter would map the planet's gravity and magnetic fields with exquisite precision, allowing scientists to peer deep inside the planet and create a detailed map of its internal structure. This information would be crucial for testing the predictions made by the giant impact simulations. The story of Uranus, the sideways planet, is more than just a quirky piece of cosmic trivia. It is a profound lesson in the history and nature of our solar system. For centuries, we viewed our planetary neighborhood as a place of clockwork precision and predictability. Uranus stands as a stark and powerful testament to the fact that this peaceful picture is incomplete. It reminds us that our solar system's past was not gentle. It was violent, chaotic, and shaped by cataclysmic events of unimaginable scale. The leading theory for its extreme tilt forces us to reconsider how planets are made. It suggests that the final arrangement of a solar system is not just about the slow accumulation of dust and gas. It is also a story of chance encounters and brutal impacts. The planets we see today are the survivors of this chaotic era. They are the ones that endured the cosmic shooting gallery of the early solar system. Uranus wears its battle scar more obviously than any other planet, its entire orientation a permanent reminder of a devastating blow billions of years ago. The quest to understand Uranus also highlights the relentless spirit of human curiosity. This is a mystery that began with a faint dot of light in an 18th century telescope. It has since been pursued with ever more powerful observatories, sophisticated computer simulations, and a daring robotic explorer that traveled billions of kilometers to give us our first close-up look. It is a multi-generational scientific detective story driven by the fundamental human need to understand the universe and our place within it. The remaining puzzles show that this quest is far from over. Our desire to know will continue to push us further into the cold, dark depths of space. In the grand narrative of the cosmos, Uranus is a key character. It is the rebel, the oddball, the survivor. Its story challenges our assumptions and expands our imagination. By piecing together the story of the sideways planet, we are not just learning about a distant ball of ice and gas. We are learning about the fundamental forces that shape all worlds, and in doing so, we learn more about the incredible cosmic journey that led to our own existence.